Hello, Chemistry of Earth and Space Science. This is going to be the video for Lesson 3. It consists of ionic bonding, but as you notice by the PowerPoint, it's literally could be a 4-day lesson. So if you broke it down into pieces, there's ionic bonding, just how ionic bonds are formed, and then a lot of naming and formula writing for ionic compounds. There's 3 different main types. There's the binary, there's multivalent, and there's ternary. Hopefully by the end of this video that will all make sense. So our goal here is to define what chemical bonding is, and specifically ionic bonds. Talk about how ionic bonds are formed, and then again, writing the correct name for ionic compounds. The terminology for the correct name is an IUPAC name, International Union of Pure and Applied Chemists. That's the body of individuals, chemists, that dictate the naming structure for chemistry compounds. So let's start here. So when forming any sort of ion or compound, the elements want to do one thing and one thing only. They want to be able to gain or lose electrons, or maybe even share electrons, in order to get a noble gas configuration. The noble gas elements on the periodic table, I refer to them as the royalty of the periodic table. Every element, as a part of the bonding process, wants to do whatever they can to become a full noble gas configuration. And what all those have in common is the fact that the outside shell, that P shell, or in the case of helium, the S shell, is full. Okay, so doing electron configurations, they would all end in P6. That means they're all going to have 8 valence electrons in that last column, 2 in the case of helium, that's the one oddball. And what this is referred to as the octet rule, meaning every element wants to get up to 8 total valence electrons. And we're only talking valence electrons here, not all the electrons. So there's 3 main types of bonding. There's ionic, covalent, and metallic. We're not going to talk very much about metallic. It's a unique situation. If you go past ATIC and come to AP Chem for some reason, that will be a small piece of what we do in AP Chem, talking about metallic bonding. But this is going to focus on 2 things, ionic and covalent. And this video is all about the ionic. So what happens? In ionic bonding, something kind of cool happens. One atom will have electrons that it doesn't hold on to very well. It has a low ionization energy. And another atom that has a higher electron affinity would be more likely to accept that electron, will accept the loose electron from the one element to the other. So if you look at this visual here, what we have on the left-hand side is an atom of, I think it's lithium. Yep, lithium. And on the right-hand side, there's an atom of 2, 4, 6, 7. That's going to be nitrogen. This is actually going to be fluorine, sorry. So the one on the left is nitrogen, is lithium. Let me see, Li, can I do it? And the one over here is going to be fluorine. Ooh, that's bad. Erase that, maybe. That's just a, yeah. Doesn't like it by writing on that edge of the screen. So what happens is, this one sole electron on the outermost shell of on the outermost shell of this lithium is lonely, all by itself, way out, and that has a very low ionization energy. So a little bit of energy comes in, it will kick that electron off and make this lithium atom become a lithium ion. And what happens when that electron is lost here, that one electron is lost, is kicked out, that means this shell, this second shell, is gone. So this shell, the one inside, is now full. So that makes this lithium ion, it's a lithium with a +1 charge, that becomes a full octet. In the case of the fluorine has 2 here, has 1, 2, 3, 4, 5, 6, 7 electrons on the outside. If it takes that one electron and it accepts that one electron, one thing is it releases a lot of energy. That's good. And the second thing is now that outermost shell is full. So what happens is during the transfer, we have two atoms that become full octets. So one of the atoms is going to lose electrons and become a positive ion, and that's called the cation. Remember when we did ions earlier, we said there were two types, there are cations and anions. The one that loses electrons, in the process of losing electrons, is going to become positively charged by some number, and that's going to be referred to as a cation. When you subtract the negative thing from the electron, it becomes positive. That makes sense. Okay. We talked about that when we were doing ionic numbers of electrons, protons, neutrons. An atom that gains electrons, well, that's what we call an anion. Again, repeat of some vocabulary from an earlier unit. If you add electrons, you're adding negative things, electrons, to the atom, and therefore the atom becomes negative. And what happens then is that we have opposites attract. If our lithium, which became charged as a +1, and our fluorine, which became charged as a -1, the plus and the minus now come together with a very strong electrostatic attraction. That process of taking those two ions and having them come together so that now the compound has a neutral charge, that is the ionic bonding part. Ion formed and make a cation, ion formed and make an anion, and then those two be electrostatically attracted. So let's look at this one. Let's look at sodium and chlorine. So if sodium and chlorine, which we've done a bunch of times, were to react, let's look at how many valence electrons each one has. So sodium should have how many valence electrons? Look on your periodic table. Tell me how many valence electrons sodium should have. So sodium, so I can draw it, sodium should have 1 valence electron. How many valence electrons does chlorine have? Chlorine, if you look on the periodic table, it's in column 7A. It has 7 valence electrons. So chlorine, 1, 2, 3, 4, 5, 6, 7. I guess it doesn't like when I do something up there. I don't know. Anyway, it has 7 valence electrons. So if we look at it like this, there's sodium and there's chlorine. Which one is going to be more likely to lose electrons? Well, if we look in the periodic table, we know that sodium is much lower ionization energy than chlorine, so sodium is most likely to lose an electron of the two. And we also know that chlorine has a much higher electron affinity, so it is more likely to gain an electron. So that's exactly what happens. The single electron on sodium is removed and is given to chlorine. Now we have a situation where the sodium has a charge. That charge is going to be a +1 for sodium and a -1 for chlorine. Now we have two ions. We have sodium the ion and chlorine the ion. And I don't want this to be too confusing, but notice here you have on the sodium, now that inner shell with all those electrons showed up. That's because once you remove that one electron from the outermost shell of sodium, you're going to have the next shell in is going to be full, which has 8. Now we have this situation where we have sodium with a plus charge, chlorine with a minus charge, and they are going to be electrostatically attracted to one another. And when they are, they form a compound. That compound is called sodium chloride. So the process where A, one atom loses electrons, B, the other atom gains electrons, and then C, the plus and minus ions come together. That's called the ionic bonding. So let's try a couple. So let's look at another combination. Potassium and iodide, and then we'll do calcium, chlorine, and aluminum and oxygen. So let's start with potassium and iodide. And I hope the pen doesn't act up on me. So potassium has how many valence electrons? Oops, get it moved down a little bit. Where are you? Where's the cursor? There. Something about when I get to the middle. Try to erase this. Yeah, let's try this one more time. So potassium, ooh, that's not laser around with that. Potassium has 1 valence electrons. Gosh, okay. I'm just gonna do it with the cursor mouse. Maybe that'll help. So, nope. Sorry guys, trying to make this as fast as possible. Gonna try this again. Okay, so we're gonna start with potassium. See how bad my handwriting is with the yeah. Okay, so potassium with its 1 valence electron, and then iodine, it has its 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And what's going to happen is this one lone electron from potassium, the metal tries to lose all of its electrons. That one electron is going to come in here and is going to grab and go into that spot. And when it goes into that spot, now potassium has a +1 charge, and the iodine has a -1 charge. And they're electrostatically attracted, and that compound is going to be referred to as potassium iodide. We'll talk about the naming in a little bit. Let's try this again. We're going to try the pen again, see if this goes any better. Okay, so we have calcium. How many valence electrons does calcium have? That's right, it's in column 2A, so it has 2. 1, 2. And now, what about chlorine? Let's look at chlorine. How many valence electrons does chlorine have? Well, looking at it in 7A, chlorine has 7 valence electrons. So what's going to happen is one of these valence electrons is going to come over here. It doesn't look when I leave it running for a bit. Okay, going to come over here and is going to give up an electron to chlorine. In the process, chlorine becomes negatively charged. It has a total of 8 valence electrons. Life is good. Calcium, on the other hand, got rid of this valence electron, but it still has 1 more. So here's the true genius of the ionic bonding. These atoms don't exist in nature by themselves. They exist as millions upon trillions upon quadrillions of atoms all together. So literally, calcium just finds another chlorine. And that 1 electron here is going to come over here, slip into that spot, and is going to cause another chlorine to be negatively charged. And then calcium lost 2 electrons, so it becomes calcium with a +2 charge. So ultimately, we take calcium with a +2 charge, calcium with a +2 charge, and chlorine, the -1 charge, but it took 2 of them. That's compound is calcium chloride. This pen is not cooperating. Okay, let's try the last one. This should be fun. Aluminum and oxygen. So aluminum has how many valence electrons? Aluminum has 3. 1, 2, and 3. Oxygen has how many valence electrons? Oxygen has 6. 1, 2, 3, 4, 5, and 6. So both of these guys have to get to be full octets. So what's going to happen is aluminum is going to take its one sole electron. Let's do this, change the color. Is it going to be dark enough? No. Let's do it again. Let's take the real light one. Okay. This aluminum is going to take its one electron. It's going to give it to oxygen. Now, oxygen has 7 now. 1, 2, 3, 4, 5, 6, 7. Aluminum has 2. So neither one of them is in good shape. But here's what happens. Oxygen will make another oxygen. So we get another oxygen with its 6 valence electrons. 1, 2, 3, 4, 5, 6. These 2 electrons up here, one will go from here and go into this spot. And the one will go from here and will go into this spot. So now this one's good. It's at -2. But now this one up top is still missing 1 electron. But this aluminum's good because it's lost all of its electrons. So this aluminum has become a +3 charge. But only one aluminum and 1 oxygen are happy. So this top oxygen needs more electrons. So what happens? We get another aluminum. So we get another aluminum with its 3 valence electrons. One of those valence electrons is now going to go to this atom here. And now this one has a -2 charge also. And this has lost 1 valence electron. So we have 1 aluminum is good, 2 oxygens are good. However, we still have this aluminum over here that's not so good. We need to get rid of 2 more electrons. The way we do that is to, once again, find another oxygen. Here's my oxygen with its 1, 2, 3, 4, 5, 6 valence electrons. And this aluminum is going to take these 2 electrons and give one of them to here and take the other one, take it around here. And when it does that, now this aluminum has lost all of them. It's +3. This oxygen has all of them. It's a -2. So what we have made here is aluminum oxide, and it took 2 aluminums and it took 3 oxygens. And this is the formula for aluminum oxide. Apologize for the pen going wacky. Hopefully you get the point. And after that lesson, you should be able to do the first of the homework pages that's just labeled as ionic bonding. Okay, let's move forward. So the next section of the notes is day 2. We talked about binary compounds. So first, if we look at the periodic table, we're going to recognize that there is a definite pattern into where atoms lie that are going to have a certain charge when they're done being part of an ion. Since this first column, where's my tablet? Since this first column has, let's see, where is it? Has 1 valence electron, all of these atoms here will graciously lose their 1 electron and become a +1 charge. Same thing here with the second one. This This column here has 2 valence electrons. So beryllium, magnesium, calcium, strontium, barium, and radon would all, not radium, radium would all graciously lose 2 electrons and become +2. And so on and so forth. So what we're going to notice, as far as the pattern goes, is that elements in group 1 will lose an electron. Elements in group 2 or 2A will lose 2 electrons and become +2. Elements in group 3A will lose 3 electrons and become +3. And on the other side, elements in group 7A will have a -1 charge because it wants to get up to 8, has 7, goes up to 8. Elements in group 6A, they have 6 valence electrons, so they want to get up to 8. They do it by adding 2 more electrons, so you have -2. And then finally, elements in 5A will want to gain 3 electrons to get up to 8. So they do. They become a -3. Now, one of the challenges here is, and this is one within your notes you'll want to color, is that there is that definite sharp pattern where you've got this first column is all going to be +1, second column all +2, third column, this is going to be below the metalloid line because metals are losers. Metals lose electrons. Metals are losers. So the aluminum is going to lose 3 electrons. And then on the other side of the metalloid line, you have hydrogen. See, here's where hydrogen can act like a metal and be a +1, or it can act like a non-metal and be a -1. So this column, they all form -1 because they all have 7, or in the case of hydrogen, 1 valence electron, and hydrogen needs to get up to 2, so it adds 1 electron. The oxygen family, or the challenges, they all need to form increase by 2, so they become -2. The nitrogen family, or pictogens, above the metalloid line, they become a -3, and the carbon under the rare situation where it would form an ion is most likely to form -4. There are also 4 other elements in the transition metals that have a distinctive charge, and that would be zinc and cadmium have a +2 charge. They would lose 2 electrons from their respective S shells to form +2 charges. Silver will lose just 1. It does it kind of in a unique way, but silver only loses 1 electron, so that's going to be +1 charge. And scandium, considering it's got 1, 2, 3 electrons, is going to lose all 3, and it's going to become +3. Everything else in the periodic table that's in gray have various numbers of charges. So we don't know them, and they'll be the topic of the next section, which is multivalent binary compounds. So what do we do with this information? Well, now what we're going to do as far as naming them, or sorry, as far as writing the formulas, is we're going to do something where we take the formula, and if we know the charge, we're going to try to make there be enough of each of the atoms to balance it out to be neutral, but also there's going to be a strong electrostatic attraction. You're going to pull them together and make that ionic bond. So what we're going to do is we're going to write our elements, our ions, formulas with the charge, and then we're going to do what's called the crisscross method to make sure that we have enough of each of the elements in the bond. Okay, let's try this. So first one is look for a synthesis of ionic compound. We're going to look at magnesium and iodine together. So magnesium, let's do this with the cursor again. Let's hope and pray. Let's see if we can do this down here. Maybe it'll let me do it down here. Come on, come on. Oops. See, it didn't let me. I'm going to yellow this time. So I have, go back, yep, okay. We have magnesium and iodide. Magnesium, if you look at its location on the periodic table, let's go back. Magnesium has a +2 charge. So magnesium plus 2. And then we do iodine. Iodine, we go back to the periodic table. We see what iodine is. Iodine's right here on this column 7A in pink, purple. And that means iodine is going to be a -1. So iodine, -1. Now comes the crisscross. So if we do this crisscross thing, what we're going to do is we're going to take the value that's up here, I'm going to crisscross it and put it right here. Not the sign, just the value. We do the same thing. Going to take this 2 that's up here and put that here. Now, if you look at it, we have 2 times 1, or 2 positives, and we have 2 times -1, or 2 negatives. So this compound is balanced. This is the formula for the compound of magnesium iodide, and we just simply be written as Mg plus 2 iodine 2 minus 1. This number right here, I call it the invisible one. Chemists as a general whole tend to not write the number 1. You've also seen on one of the previous slides, I did not actually write this charge. So it would be magnesium plus 2, iodine just minus, and then a 2. But something very, very important, you must have, when writing an ionic compound, the charges must be there. You must put charges on your ions. If they don't have charges, my assumption is you don't know they're charged particles and you don't actually see them as ions. Try another one. Reaction between aluminum and oxygen. So we already did this one, but let's see how we do it with the crisscross. So we look at aluminum. Aluminum is plus 3. Oxygen is minus 2. So we do our crisscross. We bring our 2 down. We bring our 3 down. And we get the formula of Al plus 3, 2, oxygen minus 2, 3. And look what happened. We have -2 times 3, or minus 6. And we have plus 3 times 2, or plus 6. We have the same number of pluses and minuses, so the correct formula for aluminum oxide would be Al plus 3, 2 of them, oxygen minus 2, 3 of them. Last one. Let's look at potassium and nitrogen. So we go to the periodic table, we find potassium. Potassium is a plus 1. Try this again. So potassium is plus 1. Nitrogen is minus 3. So let's change some colors up. Let's have our yellow. We take our 3, walk it down to here. Take our 1, invisible 1, and walk it down to there. And when we're done, our formula for potassium nitride is going to be K plus 3, N minus 3. It doesn't need the 1 here, but if you put 1 there, it wouldn't be penalized at all. So what we've done here is write binary formulas for our ionic compounds. Knowing the charges and knowing the crisscross method, you can write the binary formulas. And the next piece of practice in the packet is to do practice of writing binary formulas. It's just labeled writing binary formulas. Okay, so for the next piece, which is the multivalent, it does two things. It talks about naming the ionic compounds and mentions this multivalent compound idea. So let's talk about how to name an ionic compound. Well, the first things first, whatever the cation is, all you're going to do is give the name of that metal. So for instance, on our last one, let's see what we had. We had potassium and nitrogen. We would simply say potassium because it starts with K. Potassium is not multivalent. It's not one of those ones that are in the tricky spots. Let's see if I can get my cursor over there. There he is. Potassium is in a definite area right here on the far left-hand side. So it doesn't have more than one charge. So we don't have to worry about that. So then we just go to the other piece and we say, well, if that's wrong spot, sorry, too far. There. So if we say potassium, and for the second part, you're going to name the anion with the IDE ending. So this is one where you're going to have to memorize something. You have to memorize all the nonmetals and their IDE ending, because that's how you name an anion, IDE. So since this is nitrogen, this is going to be nitride. So the name of that compound we had on the last slide is just simply potassium nitride. We don't identify how many there are because potassium being a +1, nitride being a -3, that takes care of the how manys. But we don't identify the quantity, so the subscripts do not play a role at all in the naming of these compounds. Now, a couple more things that are here. They mentioned for the first element, if it's we're going to use Roman numerals if it's multivalent. We'll get there in a second. And for the second part, the anion might have a polyatomic ion name, in which case we're not going to change the name of the polyatomic ion. We're just going to copy it off the back of the table, and that will make a little more sense on day 4 of this video series. So what about this IDEs? So here are the list of all the nonmetals and their charges and what their name is. So for instance, fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide, hydrogen, when it forms a negative charge, will be hydride, oxygen will become oxide, sulfur will become sulfide, selenium will become selenide, nitrogen will become nitride, phosphorus will become phosphide, and carbon, when it does form a -4 charge, it will be called carbide. So let's work on naming some simple binary compounds. KF. K is what? Potassium. F is what? That's fluorine. What's the IDE name for fluorine? It's fluoride. So the name for that compound is simply going to be potassium fluoride. What about this one? BaO. So Ba is what? Find it on your periodic table. Ba is barium. And O, it's the second element. It's the anion. So we have to use the IDE ending with an oxygen, and that becomes oxide. So this compound is simply named as barium oxide. Next, strontium. Sr is strontium. Find it on the periodic table, it's number 38. Br is bromine, number 35. Bromine, because it's an anion, because it's part of this ionic compound between a metal and a nonmetal, it's going to be a minus charge. It's going to be a bromide. So this compound's name would be strontium, Sr, bromide. Br. And then one more, Ca3N2. So we're just naming the element. Ca on the periodic table, if we find it, it's number 20. Number 20 is calcium. And then the N. N is nitrogen. But we need the IDE ending because it's part of an ionic compound. That would be nitride. So when writing the ionic compounds formula, or naming it, you just do metal name first, anion name second. All the anions will be in IDE. Let's go the other way around. Suppose we wanted to write the formula for sodium bromide. So now we're going to take sodium, which is Na, and Na has a +1 charge. Br, bromide is bromine with a -1. So we do have the same number of pluses and minuses. We don't have to do any crisscross craziness. So here, sodium bromide's formula would just simply be NaBr. And don't forget to put those negatives and pluses on those ions. If on a quiz you refer to this compound as NaBr, you will not get full credit. You have to have the charges on those ions in order for it to be considered to be an ionic compound. Next, calcium chloride. Well, calcium is what? That's Ca. We did that on the previous slide. And its charge is going to be +2 because it's in column 2A. Chloride is over there right above bromine in element number 17, and it is in the 7A column, so it's got a -1 charge. So we have calcium with +2 and chlorine with a -1. Now we don't have the same number of pluses and minuses, so this is where we'd have to do the crisscross. So when we do the crisscross, we take the 2 from the calcium and put it down here as a subscript, and we can move the invisible 1 over, but I'm not going to. So now, in order for the compound to be balanced, I have to have 1 calcium and 2 chlorines. So the correct formula for calcium chloride is Ca2, Ca2 plus, Cl minus, and subscript 2. Keep going. Aluminum nitride. Aluminum is Al. Nitride is N. Aluminum has a +3 charge. Nitrogen, or nitride, would have a -3 charge. We do have the same number of pluses and minuses, so we don't have to crisscross. And ta-da, they come together and make the correct formula for aluminum nitride. Last one, beryllium phosphide. So beryllium is Be, element number 4. Phosphide is phosphorus, element number 15. Beryllium has a +2 charge because it's in column 2A. Phosphide has a -3 charge because it's in column 5A. So beryllium +2, P3 minus, crisscross, and then bring it together. This would be the correct formula for beryllium phosphide. So at this point, you should be able to do the next page of the packet of homework, talking about how to name monovalent binary compounds. Monovalent means elements or ions that only have one possible charge. So I have 2 more days of this to do. Let's pick them up on the next video.